I'm happy to introduce you. Martin probably knows you even better than I do. So today we are fortunate to have Maxim join us at Pulsar Coffee to talk about his latest paper on free electron lasers as related to pulsars and FRBs. Many of us know Maxim for many years since he was a postdoc at CITA. So a very distinguished history. And it's always great to hear the latest from him. And I'm sure today will be no different. So, as for a couple of notes, this talk is being recorded. I think that means that if you ask questions, you will also be recorded. And that this is as normal for our Pulsar Pulsar Coffee presentations, meant to be interactive. So do chime in, and I don't know how well Maxim is set up if somebody types into the chat window, but of course, you know, everybody who wants to participate in the chat window, that's also available.
Yeah, I won't be able to see chat quickly.
Okay, that's okay. That's okay. If I see
just
a chat,
interrupt, and I would like people to interrupt as much as possible. Yes.
Perfect. Okay, great. So take it away.
Okay, so coherent emission in pulsars, magnetars, and fast radio bursts. And I will advertise or discuss a model which is fairly new take on this 50-year-old problem of coherent emission in pulsars. And the two images that I show here is of solar flares and reconnection-driven solar flares that produce emission from radio, from coherent radio to X-rays, and a laboratory device called free electron laser that is the model will be based on this mechanism of free electron lasers. So there'll be two parts to my talk. First, I will describe the loci of FRBs. And in my mind, there is no question now that FRBs are neutron star magnetospheric events. And there is a few arguments and few predictions that were made and were satisfied. For example, radio bursts simultaneous with X-rays were suggested in magnetars, narrow emission bands drifting downward the frequency, that a radio should lead a little bit the X-rays, and that is indeed what has been seen just last year. Polarization swings within the pulse, which are somewhat reminiscent of the polarization swings in pulsars, but of smaller amplitude, and that indeed what I think has been seen. Basically, all data consisted with magnetospheric origin of FRBs in magnetars. Maybe there is something that is not exactly, but again, challenge me on that. I think all data are consistent. And this generally comes within a concept that I was advocating for some time as solar physics of magnetars. And just to highlight some of these points is, so there are two predictions of magnetars emission, radio emission before any emission was discovered. And I even said that in 2002, that one may expect the frequency drift of the peak emission characteristic of type 3 solar bursts. And these drifts have been seen, and both the rates and the range are consistent with magnetospheric origin. So this is again an old slide. Prediction of polarization swings, more complicated drift patterns, radio bursts from known magnetars that has been confirmed. And here is another old slide that shows a movie of a solar flare. And if I play, you see a slow, and you know, this whole movie takes about a day. There is slow evolution before the flare, and that's our anomalous X-ray pulsars that produce more or less constant emission. There is explosive stage. which is SGRs. There is a lot of radio type emission is generated during these events. And there was an ejection of a CME that was seen during 2004 1806 flare. So, and one more closer look on solar flares at different wavelengths. There is soft precursor evolution, and indeed, in magnetars we see enhanced activities, X-ray activities before bursts. Then there is impulsive hard X-rays and radio waves, microwaves, and then there is a soft tail, and all of these parts are seen in magnetars and FRBs. Another argument that I think is very strong. We know that X-rays and gamma rays are clearly magnetospheric events because we see oscillations with the known period. And we have a coincidence with the radio down to few milliseconds. So radio is magnetospheric too. And actually radio leads X-rays by a few milliseconds, which is what you expect. And primary peak of these giant flares is very similar to regular magnetar bursts. And actually the burst that was seen in radio is exceptionally hard. So it's very special type magnetospheric event. Another interesting relationship. This is a very strange plot that solar physicists use. They plot X-ray luminosity versus radio flux, which have different dimensions. Still, that's their standard. And they plot it in the lower left corner is they start with nanoflares for solar nanoflares to very large flares on stars. And then if we put our SGR 1935 on this plot, this covers 20 or something orders of magnitude, and the correlation is kind of almost there. And actually it is off to the right side, off to the right side in the sense that the radio is slightly more bright that you would expect from this correlation, because now we are talking about coherent radio. Well, all this is non-thermal but non-coherent. Also periodicity, and so this is the abstract of a paper that we published just 2 weeks before the discovery of FRBs from magnetars, and we said that at the very bottom, the observations consistent with magnetically powered radio emission and generating in magnetospheres of young, strongly magnetized neutron stars, the classical magnetars. And basically here we are saying that periodicity observed in a couple of systems is not intrinsic to the source, but is a propagation effect because our neutron star is in the binary. And by the way, recent low far frequency observations can be accommodated with some modifications of the parameters because they have a very steep density gradient in the wind. So it quickly becomes transparent even at lower frequencies. Now, going a little bit back in time, after the discovery of the repeater, I was arguing that only magnetospheres of neutron stars. And basically, with the repeater, we know the distance, we know with the flux, we can estimate the radiation energy density at the source. And then we can ask what would be the equipartition magnetic field. And that would be the lower limit on the magnetic field. And the equipartition magnetic field is almost 10 to the 9 Gauss. So these are neutron star magnetospheres. And we already know that they produce radio emission, they are clean, relativistic. So there is a strong point about magnetospheres of neutron star that was made almost 5 years ago. Another subtle point is here we are talking about very bright radio emission, coherent radio emission. But any particle that produces this coherent radio emission would also suffer from normal losses, normal like synchrotron and inverse Compton. And then if you use the usual parameters for unmagnetized plasma, you will deduce that this laser intensity parameter A is huge, 10 to the 6. And 10 to the 6, that would be the Lorentz factor of a particle producing that radio emission. But that particle would experience horrible normal losses without magnetic field. But with strong magnetic field, the important parameter now is not the laser intensity parameter, but just the ratio of the wave intensity over the guide field, which is small. So the conclusion is that large magnetic fields are required to avoid catastrophic normal losses. Another point, interesting, that repeater cannot be rotationally powered because basically that would exceed the spin down power. Right. So it cannot be rotationally powered. But here, again, it's this old slide from years ago. Here I say that magnetically driven is okay by energy. There are some observational limits at that time, but that's important. That's very important that, yes, it's not rotationally, but magnetically driven. And another point is we have associated X-ray burst, and that should originate close in by energy requirement because the X-ray burst requires 10 to the 41 ergs, and the time alignment. So that energy density and the shortness require a large magnetic field. Basically, you need a football field of magnetic field in magnetars. And the time alignment between radio and X-ray also implies that in radio we generate emission close to the neutron star surface within, at most 10 to the 8 centimeters. So, conclusion one. As I outlined, I think all, and please challenge me on that, all observations are consistent with magnetospheric origin of FRBs. Temporal coincidence, radio leads, frequency drift, polarization swings, all predicted and confirmed to various degrees. Any questions before I go to part 2, the mechanism?
I see a question from Jason.
Am I allowed to ask a question? I don't want to.
Oh, please do. Yes.
Yes, you
okay.
are. You're now honorary group member.
Okay, thank you very much. So Maxim, yeah, I think a lot of this makes sense, but I think one important thing to keep in mind though is that you shouldn't necessarily be mixing repeaters and non-repeaters. You show like the X-ray radio ratio from 1935, which is an isolated source. Could be a repeater. Well, it probably is a repeater because we've seen a few bright-ish bursts from it at least. But then these repeaters, they have different. It seems like they have different radio bursts, wider radio bursts, more of this drifting effect. It's not obvious that they're the same detailed emission mechanism as the non-repeaters. And I think this periodicity, it's hard to believe that the periodicity, the 16-day periodicity in the case of R3 is really, it's an orbit, but that's just a red herring, that it doesn't matter. It seems like it has to be involved in at least stimulating explosive magnetic energy release from the neutron star. I mean, that is just pure coincidence, seems unlikely to me.
And so as we've been discussing this a little bit, I don't think it can stimulate emission in the following the next argument. Again, if we invoke the binary the double pulsar, where we see how pulsar A influences pulsar B emission. But that pulsar B is exceptionally slow and weak, meaning its magnetosphere is huge. And then the power of the wind of the pulsar A is actually comparable to what we expect of the powers of from B stars, 10 to the 33, 10 to the 40, 32, in that range. That means this wind from the companion, in order for the wind from the companion to affect the magnetosphere, it should be a very kind of slow and slow magnetar. And that will be very, very strange that, you know, Pulsar B, of the double Pulsar B, died because it's so weak. We wouldn't have discovered it. And to argue that these dying magnetars or dying pulsars produce the most bright emissions, radio bursts in the universe. And on top of that, you know, magnetic field pressure scales are to the 6. So any influence that the wind can do on the magnetosphere will be very limited to the very, very outskirts. And as I was arguing, from energy constraints of X-ray bursts and time coincidence between X-ray and radio, this must be closer than, say, 10 to the 8 centimeters. And by 10 to the 8 centimeters in magnetar fields, no wind will penetrate that deep.
And yet, I mean, okay, so I understand these arguments, Maxim, but it's not just the fact that it's possible to get low far frequency radio emission out from R3. The fact is that one sees emission at those low frequencies at later times in this activity cycle, but then not correspondingly at high frequencies at the same times. So why is the emission pushed to be at lower frequencies at later time?
I don't know. It is an argument.
My sense would be that I thought your talk is mostly going to be about how the emission is generated.
Yeah,
I think I'm actually really curious about that, and I share Jason's doubts about the interpretation of R3, but I have no idea about the emission mechanism, and I would really like to hear about that.
Yeah. Okay. Go ahead.
Is it okay if I briefly chime in? Yeah, so Dongzi Lee, Wei Pen's previous graduate student, and I recently wrote a paper about how you can incorporate, maybe not in terms of the binary comb model, but in terms of just magnetospheric origin, all the observations you're talking about if the emission is just due to coherent curvature radiation. So, I mean, I'm not going to take up the space, but it's possible to incorporate all of these things within a magnetospheric origin of a neutron star. But
yeah, I think your emission mechanism is actually not so relevant, right? It's mostly a geometric argument. So I'm going to be a little bit insisting, because I tried to read Maxim's paper. I did not completely understand it. I understood enough to be really interested, and I think we really in R3, I don't think we know the answer yet. That's quite clear. And I don't think
the answer for this is a bit of a detail, I think, for all of these discussions about what's coming next. So I think it doesn't actually matter for Maxim's next step.
I think it does, but let me make one comment here. When we talk about coherent emission of centimeter wavelengths, we're talking about coherent addition of phases with a precision of 1 millimeter or so. And then if people try to put it in the context of this coherent addition of phases, we don't talk about energy, it's just pi over 3 and pi over 2 on a scale of a millimeter. And then when people try to connect it to the magnetospheric scales of hundreds of kilometers, it's a treacherous path that is definitely wrong. It may be a simple one because, say, coherent emission by bunches, 50 years of research, and there was a definite conclusion that it doesn't work yet. It's a popular model because it's very appealing. Let's assume bunches are created and we calculate everything. But if you think about how you create a bunch of electrostatic repulsing charges, It's a big question that people cannot answer for 50 years. So, but let me discuss how I think bunches indeed could be created and the mechanism. An anecdote. So 25 years ago, when I started my PhD prelim exam with a slide saying, pulsars were discovered nearly 30 years ago, but we still don't know pulsar emission mechanism. And Roger Blanford and Peter Galbraith, who were on my committee, they both laughed a bit uneasily. And since then, I regularly corrected 25, 30, 50 years. So it was starting to become uneasy for me too. But I think I have a very good argument here. So first, also echoing Jason's that there may be several emission mechanisms. We know that there are several radio emission mechanisms in pulsars. For example, Crab, main pulse and interpulse, and the precursor have different. And an important point that I'm making is that Crab main pulse and interpulse are reconnection driven just outside the light cylinder, not rotationally driven, because so far we've been mostly thinking about rotationally driven. And then that unites Crab, Magnetars, and FRBs, that the source is not rotation, but reconnection. And this is kind of a slight bit of a change of a paradigm. Reconnection driven, not rotationally driven. Okay. And one of the key points that were guiding me through all this research is narrow bands. We see narrow bands in Crab and in here on the left, and in Crab, not in all parts. So it's called high frequency interpulse, and there are dozens at least of fairly bright, almost equally spaced almost equally spaced. They're unequally spaced by 6% in frequencies. But they are, as you can see on the left, they are nearly all bright. So and there is dozens of them, Then there are narrow emission drifting bands in FRBs. And then there is solar type 3 radio bursts that also have narrow drifting emission. So that was my challenge.
So Maxime, what is the scale on the solar type thing? Is it? I mean, I think it's just to have a sense of what, like, because those I've never really seen. That's my fault, of course.
It's minutes at most.
And in frequency, is that just orders of magnitude, right? It's 10 to
the 6.
So
here it goes from 10 to the 7 to 10 to the 5
hertz.
10 to the 6, yeah. 10 to the few 10 to the 4.
Right.
Yeah. Over time of minutes. So this is very subtle feature of emission, not overall whatever. It's so I took it as a main challenge to produce narrow bands that can be equally spaced, can be drifting. On sometimes there is no narrow bands but broadband emission. And here is the model. It's a working model that in laboratory lasers, it's called a free electron laser. And the idea is the following. You start with a highly relativistic beam of particles, and then you put magnets. And the magnets, they alternate polarity. And then this beam oscillates in this magnetic field. And also, since magnetic field doesn't do any work, the total velocity of the beam particles is constant. But since there is oscillating velocity, the axial velocity also changes, oscillates. And then by charge conservation, there should be density fluctuations. So, and this basic mechanism creates particle bunches that oscillate and they emit coherently. And what I did the most of research is that I adopted this process to the guide field dominated case, meaning when there is a strong axial field that dominates everything. And then the way I imagine it's working is, so if we have magnetosphere, there is some Alfvén waves that's shaking the magnetosphere, and that's the wiggler. And then there is a reconnection generated beam of particles that produces coherent emission through this free electron laser. Similarly, in Crab, we have this reconnection sheet just outside the white point. There is a wiggle magnetic field and a reconnection driven beam of particles. So, and again, bunches are induced in the beam by the wiggler, and they emit coherent collectively. This is a little bit of a repetition of what I already just said. So we have a strong field which is wiggled just a little bit. And the beam goes along this wiggled field, generates bunches, and these bunches emit coherently. Okay.
Maxim, just really, since this is probably the essence to get right. So I can easily see that I have a magnetic field which just gets perturbed a little bit. So there's these waves going around, and you're adding it to that. Right, there is maybe generally electrons going, but what makes a burst is that you have a sudden extra release of a lot of electrons which go along this.
Right.
Is that right?
Right.
Okay.
Right. So yeah, there are two parts to the FRB, the way I see it. First, there should be a wiggler, shaking of the fields. And second, there should be a beam of particles that goes through that wiggler. Yeah, yes, very good. So there is a few technical details that I would like to outline. And the model is fairly complicated. It's second order expansion and weak turbulence. You need to calculate particle motions. You need to calculate phases of the waves, add them coherently, then average those phases of a particle distribution and wiggler wavelengths, and all of this in a second order in perturbation theory. So it's pretty tricky, but just a quick outline. And actually, my son wrote a Boris code in Python. So Boris code, that's a common way to integrate particles motion in electromagnetic field. And here we show how particle in the beam frame moves in a strongly wiggler, in a strongly guide field dominated regime. So on top left is this 3D rendering of the particle trajectory. Then on the top right.
So which is the direction of the magnetic field, or is that
magnetic field is in Z direction, but the axes here are very different. As you can see, X goes from -20 to 20, right. Y goes from 0.6. So this is a highly elongated kind of twisted figure 8. Okay. So it's a twisted figure 8. And the way we actually achieve it is kind of because we need to keep phases, and we cannot just start a wave. We need to add it adiabatically. And the picture on the right shows trajectories in the XY plane when we turn on the wave, and you can see that it slowly reaches the final trajectory. And on the bottom, beautiful figure 8. Each of them is composed of, I don't know, 10 or 100 separate trajectories. So that tells us that we keep the phases very well. And for coherent addition, phases is everything. Yes. So, and again, if we go back to this picture, if we have a wiggler, we expect the density in the beam will be oscillating on the double frequency, because yeah, on the double frequency. Basically, every time the beam gets perpendicular velocity, the parallel velocity slows down. And it gets perpendicular velocity up and down, but in both cases, the parallel velocity slows down. And this is indeed what we've seen. So on the left, we see two phases in the beam frame. And we have this, and on the right is just the slice at some given time. And you clearly see two density enhancement per period. And the trajectory here are well resolved, meaning that they do not intersect. So we track the particle motions pretty well. Now, this is the key part, and it's really tricky. So what you need to do, you have beams, you have particles that initially are distributed homogeneously. And if each particle emits independently, if there is no bunching, the phases will add up randomly. It will be incoherent. So here, the coherent addition is really tricky. So first, you need to calculate the retarded amplitude from each particle, then average that over time and phase and distribution, and then square it to get intensities. And all of this is done in a square, a second order in a small parameter. So on the left here, what I plotted is the solid line. So this is a harmonic wiggler, harmonic linear polarized wiggler. Solid line is a coherent addition, dashed lines is an incoherent addition. And you can see that, and that's in a beam frame or normalized to the wiggler frame, to the wiggler magnetic, to the wiggler wavelengths. Anyway, there is enhancement by a factor of 200, and that's indeed what I expected. So the difference between solid and dashed is the coherent addition of phases.
May I just ask if I have the right picture, mental picture of what is wiggling here? So if I have a so in a free electron laser, as you already pointed out, there are two things. One is I have the trajectory of any given electron is wiggles. But of course, if I just had a constant current, that doesn't, you've got no time dependence, that doesn't help you. So then you, in the case of in a lab thing, well, you can bunch them before you send them in, so that's easy. In your case, they self-bunch, I think is what you're proposing, and the self-bunching is presumably due to some collective interaction of the particles with themselves. So you have an external field, and then you also have some self-interaction of the stream.
No. I will actually discuss that in one or two slides. Can I?
Yes, of course. Yeah, please do. Please continue.
Yeah. Okay. So so going back to coherent addition of phases. So for harmonic wiggler, but what I was surprised then what I did, I sent a Gaussian pulse, which is a short pulse, which is composed of many waves. And what I see here on the right is that the Gaussian pulse also can give coherent addition for the waves for the emitted waves with the wavelengths longer than the duration of the pulse. And that kind of makes sense. As the Gaussian pulse comes in, it creates a bunch, a charge bunch in front of it. That charge bunch oscillates, and that charge bunch emits waves with a wavelengths longer than the width of this pulse coherently. And that's a very strong point, that that means that the wiggler should not be highly harmonic. It should still be limited in spectrum, but very mild conditions. And here is plasma effects in the beam. And that's one of the key points. So the density fluctuate charges are created by it's a single particle process by the Pandering force. Okay. Then you can ask whether plasma effects, so you create charge bunch, but charge bunches would like to repel electrostatically. The question is, do they? The answer is no. There is modification. So first, parallel driving can be as vain as any omega. There is no cutoff.
Since I had to look it up, and I'm sure not, I mean, some people are probably too shy to ask. I mean, I did not remember what ponderer motor force actually is. It makes you go to Wikipedia tells me it makes you go to weaker magnetic field strength rather than oscillate. Do you want to?
Basically, in this context, if you have a wiggled field, and again the total velocity is constant, then the z velocity changes. And then if you ask what is the force that makes the z velocity change, and that force is called ponderer motor force. And it comes out as a second order expansion of particle motion. But that's the explanation. So
can I ask a quick question, Maxim? Quick question. Yeah. I mean, in lab FEL, you get bunching when you are near resonance, FEL resonance. So you know, a lab FEL is tunable.
Yeah.
So what gets you the resonance condition here? I mean,
there is the difference. There are several subtle differences between this and the lab. For example, the lab prefers circularly polarized wiggler, and in circularly polarized wiggler there is no bunching, and in the lab the bunches are created due to the radiation reaction force typically. They don't like linearly polarized wiggler because that has a large drifts, so the beam hits the wall. And the conditions of the guide field dominance is basically, it's very hard to satisfy in laboratory conditions. But the resonant conditions is the same as in this case as in the other case. It is, you can think of this process as induced scattering. The wiggler is in the frame of the beam. The wiggler is almost like electromagnetic wave. There are bunches that coherently, that induce scatter this wave. And by the conventional Compton formula, the observed frequency will be gamma squared times wiggler frequency in our frame. So it's gamma going to the beam frame and gamma going to our frame. And I'll mention it in a second. But I would like to come a step back to Wei Li's question. So the collective effects, though I haven't done peak simulations yet with the collective effects, but analytics says that collective effects will change the driving, but not the amplitude of the driving, but not the phase of the driving. Now, as I said, so many things match. You have a harmonic wiggler, you expect multiple stripes. And that's what is, in mathematics called Jacobian expansion of Bessel function. Multiple stripes, equidistant. And that immediately calls for, reminds of Crab pulsar. Now, there is a subtlety that in linear regime, you expect these stripes to be equally spaced. But then first, there is a question of saturation. And also, if you have nonlinear driving, like Matthews type equation, you expect also this, what's called the tons, to be not equally spaced and increasing with frequency. Polarization. And here, Jason really was helpful. Harmonic wiggler need to be linearly polarized to create bunches. Because if it's a circularly polarized, the particle, the beam just goes with constant velocity. It must be linearly polarized to create bunches. That creates stripes. And that produces linear polarization. So there is a clear connection between spectral and polarization properties, stripes, linear polarization. On the other hand, if you have just a Gaussian pulse propagating, a broadband, That can have arbitrary polarization because there is one bunch right in front, and it can produce, it can be linearly or circularly polarized. So stripes linear, no stripes any, and that matches. Another point, the saturation of coherent process. And this is a highly tricky question. And basically, I warn you not to believe anyone who claims that he can calculate saturation of a coherent process. That means he can calculate how these phases add and then start to counter react to their coherent addition. Really tricky. Yet, if I just plug, and if I just assume that fraction of the energy of the beam goes into radio emission, I reproduce brightness temperatures in FRBs of the order of 10 to the 40 and in crab few times 10 to the 33 without any fine tuning. Duration from microsecond to milliseconds. As I mentioned, you need a football field of energy. So that's one of the hundredths of a neutron star radius. So duration can be from a light travel over 100 meters, which is microseconds, to 1/100th of a period if your engine works long enough, but you emit along different directions as the system rotates. So that match.
Maxime, what sets the, in a nutshell, what sets the difference between the CRAP and the FRB? Is it just the magnetic field, or is it, I mean, I trying to, I mean, your scalings don't tell, basically. So
yes, that's my next slide.
Oh, okay.
And I think that's that also answers Amir's question. So the theory is really sturdy. It can tolerate fairly large dispersion, both in the momentum of the beam and in the spectrum of the wiggler. That was a bit surprising. The frequency is gamma squared times the wiggler frequency. Importantly, this frequency is independent of the magnetic field. So it works in millisecond pulsars and magnetars and far out in crab. And also, it is fairly insensitive to the wavelengths of the wiggler. Basically, in a magnetar, you need Lorentz factor 10 to the 2, because your size is of the order, or your wiggler size is of the order of a neutron star radius. But for crab, you need a 10 to the 3, because you are, 100 stellar radii out.
So just a conceptual question. So you're envisioning high relativistic Lorentz factor of 100 to 1,000 electrons moving along a wiggled field line and causing radiation. Now, these field lines, I guess you're envisioning have to have a rigidity that exists independent of the electrons. So what supports the field lines? Because otherwise, if the whole thing just flows out, there's no relative motion between. So how do you get a relative motion between the field lines and the electrons?
So this is more or less a next step, but there are two things that I have in mind here. One is that excitation of these alpha waves and generation of the beam are two independent processes, meaning there is always some jitter in the magnetosphere because things always do something funny. And then at a somewhat different region, there is a reconnection that sends a beam through this jittering magnetic field. On the other hand, this jitter can be self-generated due to fire hose instability of the beam itself. This is a little bit more complicated process so the leading part of the beam becomes fire hose unstable, generates the waves, and the following part of the beam kind of scatters those waves, induced scatters.
Okay, so just see if I follow what you're saying. So you envision two populations of charges, one that's responsible for making the guide magnetic field, and another set of charges that's actually radiating.
Yeah.
And these two move at different velocities relative to each other.
Yes, good question. So there is background plasma. So this whole thing is a background plasma, and these wiggler waves are actually Alfvén waves. So this is the first component. And then on top of that, you shoot a beam, a highly relativistic beam of particles. There is also a question how this background plasma would affect the beam particles. And I make an argument that it probably doesn't because of Lorentz factor suppression, even though
Can I follow up on this?
Yes.
The point here is that the energy density in your beam cannot exceed the energy density in the Wiggler field. Otherwise, as was claimed, you cannot actually, self-current.
Energy density in the field is much smaller than the energy density in the Wiggler field. Much smaller. Because you see, you have a critical magnetic field 10 to the 14 Gauss. If you wiggle it with amplitude, I don't know, 1 millionth, that's your fluctuating field is mega Gauss.
No, but you are limited by the plasma frequency. You need the plasma frequency. And even if I take a multiplicity of 1, your plasma frequency needs to be below, below gigahertz, right?
Yes.
So your magnetic field has to be, below something like 10 to the 8 Gauss. So it works for most system, but I don't think it, for the bright FRBs, it's a problem.
No, I don't quite agree with you, because here we're dealing with Alfvén waves, highly magnetized. They're almost like light waves. So the background plasma we briefly discussed it, and I thought so again, the energy density in the Wiggler for any parameters is huge compared to any energy density in radiation. And it is huge compared to energy density in the beam. And as I mentioned, if I can convert all the energy density in the beam to radiation, I match the brightness temperatures. But basically, the effective A, the nonlinearity parameter for Wiggler fields, would be times like 10 to the 16, while the effective A for the radiation is 10 to the 5 or 10 to the 6. So, and the energy density scales are square of that. So the energy density in the Wiggler is absolutely dominant. And I don't use it. I use the energy density of the particles. The Wiggler is just basically a static cold wire that is sitting there. But that wire is so strong that it's not get destroyed by the beam. So I hope I answered. There is also cute ideas that if you have several Wigglers, the bead can be very efficient. So that's what I just mentioned. So origin of Wiggler, shaking of the magnetosphere. And then I also made a model of these Alfvén waves in the.
So this is Maxim, maybe just a general question again. When you want this beam anyway from reconnection, it sort of seems natural to also let that do the shaking, or is that just energetically impossible?
It is possible. Yes, it is possible. Yes. And I discussed it separately. Yes, yeah. Or, for example, when people do peak simulations of reconnection, they often see somewhat different population of particles. Maybe a very, very fast and light beam and a slower but heavy beam. And one can imagine that slower and heavy beam does fire hose, while the fast light beam is does the emission. And then, as I mentioned, so it's quite cute. It's alphin soliton limited both in axial and transverse direction. So you can find some interesting solutions where, as it propagates, it rotates like as it propagates, it rotates plasma, counter rotates. Yeah. So radio emission is generated due to initial stages of magnetospheric reconnection events, while the magnetosphere is relatively keen of pair loading. Initial stage of the gamma ray flare, 200 microseconds. It kind of matches the duration. And the overall duration, I already kind of discussed that. Challenges. I already mentioned, of course, you need to do peak simulations. Why giant pulses only in crop and few other milliseconds, not clear. And then why repeaters with narrow emission? So the larger scales. And I would really advertise against the idea. So here is, it's a screenshot. We assume that bunches are generated in Pulsar. It's been 50 years. You cannot assume that. People couldn't make them for 50 years. You cannot assume that. Basically, let's not cheat the 50 years of hard work, that hard thought that people put into that. So let me pause here. I'm done.
Maxim, who was saying about this? Let's assume bunches are generated.
I should not have. Yeah.
Hi, Max. Can I ask a question?
Sure.
So in the crab case, there is some evidence, or not evidence, but previous theories have argued that the giant pulse emission comes from the reconnection current sheet outside the light cylinder. In that case, I find it hard to imagine where the guide field lives, because by symmetry there is no guide field in the reconnection region. So the particles should be shooting somehow through without the guide field. Do you really need it? Because in the reconnection region, the field goes through zero, right?
Right. It is, for example, yeah. So can you see my slide now, right?
Yeah.
So the way I draw this crab Y point, I wiggled the current sheet, and as Anatoly points out, that will not have a guide field. On the other hand, if you reverse the direction of the electron beam and shoot it back into the magnetosphere, it will quickly reach this Y point and will start going along strong guide field. But yes.
Right, but in terms of phasing, I think you needed to align with the gamma rays, and that all works for the outward going thing in the wiggling reconnection layer going outwards, right? Not
right. Right. So again, in laboratory, all these FALs work either with no guide field or with weak guide field.
Mm-hmm.
So yes, it can work. The challenge for me was to make it work inside inside magnetar magnetosphere in a highly dominated.
So you think the Spicer orbits in reconnection layer can work as an FEL?
Yes, if in one of our simulations that Yegor did with Boris Pusher, we see if the field is very strong, the particle oscillates like that.
Mm-hmm.
If you decrease the strength of the field, it starts doing a spice orbit in perpendicular direction. And if the field, and then eventually it becomes circular, something like that, yeah.
Okay, but we've done big simulations of connection layers for a while now, and we haven't seen this. We haven't seen bunches of electron beams flying through plasmoids. They're all trapped. They're all confined. So there are accelerated particles, but I haven't seen any like laser guns pointing at us. Something that we should, we certainly can look for, but tell us what exactly we're looking for, because we may have missed it before, but it didn't jump out from simulations.
Right. So I think
if I could just very quickly, another short question. So you mentioned that these alpha waves are they standing waves or are they moving waves? If they're moving at speed of light, then
yes, they're moving waves at the speed of light. Yes.
So aren't the particles and also moving at speed of light? So you have to worry about them kind of going in the same direction, or are you interested in counter moving?
I did very detailed calculations for static wiggler. Then I did a then I did Lorentz transformation of a static wiggler to the particle frame.
Mm-hmm.
And for highly relativistic particle, what it sees in its frame is basically an electromagnetic wave.
Just if I may ask Anatoly, if you have an alpha, is the alpha, these two things are only they're only going at both the speed of light when your alphane vector is exactly parallel to your B field. However, if you take a random other directional alphane wave, it'll be going as half the speed of light, which might as well be rigid in terms of a relativistic particle moving with the field line. So perhaps there's the few modes that are exactly parallel. This might not apply, but I don't think Maxim cares. Any alphanic wave at any angle will do the trick.
But also I am thinking about alphane wave going to the left and particle going to the right.
Okay.
So
but there is some
in that case,
need,
particle
right?
doesn't care whether it is alphane wave or electromagnetic wave.
So ultimately, what is the wavelengths of the waves that you really need to explain what we see?
A fraction of the radius.
Fraction of the radius.
Well, isn't in your
and
case
a fraction, and that's where this Lorentz factors come in. If you scale it with a neutron star radius, you need Lorentz factor of 100. If you scale with the light cylinder radius in Crab, you need Lorentz factor of 1000. And these are kind of low Lorentz factors by Pulsar standards. But going to a previous question, yeah, I think the system is complicated, fairly complicated, that in order to find signal, you should be kind of set up your models to look for that signal, and it will not jump out from other simulations.
Thanks, very interesting.
Maxim, can you handle gamma of 10 to the 4? I mean, as you know, we think we have evidence for that. I mean, I'm quite happy to have your bunches create a banded spectrum, but I would like it to move a bit faster.
This doesn't exclude gamma 10 to the 4. It will just produce too high of a frequency. And then you will get, so here again, I am scaling it to something like 1/10 of a radius. And then if gamma 10 to the 4 will be able to handle longer wavelengths, but then it's not just a simple harmonic wave.
Well, I think
this does not exclude gamma 10 to the 4, but it doesn't need it to produce gigahertz emission.
No, but I think if I follow your picture right, that if you say that, for example, that our Crab lensing evidence requires Lorentz factor 10 to the 4th, that means that your actual K of the alphane wave has to be 10 to the 8 times the wavelength you observe at, so 10 to the 8 meters. That's what you wrote, gamma squared k. And that just means that this emission would have to happen, many light cylinders out, because otherwise you don't have enough space to create a wavelength.
Yes, yes. Yeah, I agree. And again, putting it into global context is very difficult because, again, we are going from millimeter phases to a large scale.
Well, you don't actually need millimeter phases, right? Because
oblique alpha waves may help, yeah.
But you only need to be coherent to a KC. You don't need to be coherent to the omega because it's all Lorentz boosted.
You need to be coherent to the gamma KC. You need to be coherent in the frame of the beam.
Yes, but not gamma squared.
Yeah, but not gamma squared, yes. You need to be coherent. And that's actually what saves you, because you need to be coherent just in the frame of the beam, and that's kind of easy. That's exactly the first line here that this is exactly that.
Right, you might have naively expected that it would have been delta k over k of 1 over gamma or something like that.
Yeah, but actually, and for the momentum, if all the motions are non-relativistic in the beam frame, then you're okay. Yeah. Yes.
I actually think that this is too loose statement in terms of delta p over p less than 1. I actually think, well, that's coherent emission, right?
Yeah.
And for coherent emission, you have a number of cycles to have the amplification become significant.
Yes.
So instead of 1, you should actually you should put n, the number of cycles. Yeah. So if you talk about, say, amplification by a factor of 1,000, you need about 10 e-folds or so. I mean, just 10 or 20, I don't know, something like
correct. All agree. Yes, the Landau-Pomeranchuk effect and so on. There is a subtlety here, very funny. This is delta p over p less than unity in our frame. That means delta p over p in the beam frame is 1 over gamma. So yeah, if you have a mildly narrow distribution in our frame, still it should be narrow. Otherwise, you won't get anything.
I always thought that it's going to be in the frame of the Wiggler. So this is in the frame of delta k over k. Where, I mean,
but Wiggler is our frame. And in the beam, basically, if you do Lorentz transformation of what's the relativistic distribution, thermal distribution factor, Maxwell Eutner, you will see that if the dispersion in our frame is less than unity, then in the beam frame it is 1 over gamma of that.
Right. Well, I kind of agree with that, but still, delta k over k is also has this constraint that you have to have multiple cycles, and that one that you have in delta k over k is also should have. I mean, regardless of the beam, I mean that this is just the coherence in terms of the Wiggler field.
Absolutely. These are the questions that I was asking myself. That's why I did all this numerics. I did all these coherent phase additions. Yes. And well, for example, here on the left, this sidebands is due to the length of my integration domain that introduces these things, and I can make it narrow. So yes, this is all correct, and I think I did a careful analysis of this numerical. Yeah.
Okay, so how many amplification cycles do you have in your simulation?
Well, as I say, well, basically 200 here for the harmonic Wiggler.
Okay. So in that case, delta k over k is about a percent, a fraction of a percent.
Yeah. Basically, what I think Misha is saying, that you cannot treat it as a curvature emission in wiggled field.
Mm-hmm.
It is not, because this is called Landau-Pomerachuk effect. There is a radiation formation length, and that is fairly long. And the electron changes its motion on scales much smaller than the radiation formation length for the curvature emission. So it is not a it is not a curvature emission. But it is induced scattering.
So again, I just follow up. I mean, the amplification length is larger than the stellar radius, typically in the star frame.
Well, this is I mean no,
because that would mean that your magnetic field changes, you know, along the beam. It's not fixed. So I mean, how you keep it going?
So basically, so this simulation that I of course do as a simple constant guide field.
Yeah. But in reality,
here I do not address the global structure, and of course the global structure will mess up things. And I agree, and that needs to be looked in a more detail, but this is a little bit beyond the simple code that I have, I think. But in principle, yes, what Amir is saying, that if the Wiggler wavelength becomes comparable to the radius, then things will start to get also out of phase. Yeah. And that actually may help under certain conditions. In laboratory FALs, sometimes they do get tapered Wigglers. Yeah, so it's not necessarily that it will hurt. And also, you know, this should not be like a laboratory device where you come and press the button and it works perfectly. You can wait for 100 rotations, and then good conditions appear, and then you get a burst.
Max, do you predict it to be all over the sky, or is there a particular phase that it would shoot at?
This is again a question of global structure, which here I do kinetic, and it's very dangerous to put the simple kinetic calculations in the global picture.
Well, that never stopped you before.
Yeah. No, I cannot. No, I cannot at this point.
I did have a conceptual question on the transverse structure of this. So presumably, and it goes back a little bit to what Anatoly was asking. So presumably the transverse size must be at least as large as the gyromagnetic radius of the electron. So if you have a strong guide field, this can be microscopic and everything is going down your guide field.
Yeah.
In the case of the crab, imagine you've got some reconnection event, ejects a lot of highly relativistic electrons, and those are now, well, I guess now the question is, do they stay very, very localized transversely?
Yes, very good question. So they definitely stays very localized transversely in the magnetar case. That's absolutely impossible to excite. In case of and they also stay localized transversely in a typical magnetic field at the crab light cylinder, because typical magnetic field of the crab light cylinder is something like 10 to the 6. So cyclotron frequency is whatever, 10 to the 13. You multiply it by gamma squared, you're way out. But as Tolik pointed out correctly, in the current sheet, the guide field may be much smaller, And that brings a whole new, well, that brings us back to the models of free electron laser with small guide fields or negligible band fields. And actually things can be much more efficient there with small guide fields. If you can excite gyration, that basically increases coupling between your wiggler and the beam. And under certain conditions, increased coupling means that you can convert beam energy into radiation more efficiently. So yes, there are. This has been addressed in conventional free electron lasers, the effects of the cyclotron resonance. So this is kind of done and known, and the answer is it could improve operation of FAL.
Okay, beautiful. By the way, I'm afraid I do need to attend another matter right now. Everybody should feel free to continue. I just will have to apologize myself.
Yeah, I have another question if I can.
Yes, go ahead.
On this graph, you show the frequency, I mean the power spectrum basically, right? Especially yes. on the right panel. That's the logarithmic scale. Am I right?
Yes.
If these are the bands, okay, well, the bands we know that they go from probably half of gigahertz up to 30-ish, even more, 40 gigahertz. Yeah. So it cover about almost 2 orders of magnitude, right? Yeah. So if I look at your spectrum here and starting from 0.5, for example, where it's roughly 1, and going to 5, which is exactly an order of magnitude, it goes down by a factor of even more than 1,000, almost like 10,000.
No. The Gaussian pulse would produce low frequency main pulse and interpulse, which is broadband.
Okay.
The harmonic wiggler will produce, where is it? The harmonic wiggler will produce many emission bands. And again, the Gaussian pulse will be producing broadband at lower frequencies, while harmonic will be emission bands at higher frequencies. That's consistent with what we see in Crab.
So Maxim, what would be physically different? Do you think you have an idea about what the physically different regions would be that where sort of one thing is happy to happen and
yeah, good question.
I don't know. Yeah.
Okay.
I don't know. I don't know.
But I guess from your earlier statement, in a way, the fact that the main pulse and interpulse, if they're indeed outside of the light cylinder, and I thank Anatoly a lot for his simulations because I feel they changed my mind about how things work. And could it be that these ones are more inside the magnetosphere where you have a stronger guide field and so on?
Yeah. Yes. Yeah. Putting this microphysics in a global context is complicated. Yeah.
Can I still beat the same horse again? And yes. Just okay, in this graph, we go from over 100 down to a few within a range of 20, which is roughly the range of the band. Do we see actually such a change in the intensity?
No. Here is what I'm saying. This is for single particle emission. So this is, and on top of that, you should add coherent addition from different particles. Plus, this is for very weak linear driving. So then the separations are equidistant. And if you think about, again, in terms of Matthews equations, nonlinear driving would give you larger separation. But you pointed out correctly that here we are changing by a factor of 20, and our driving decreases by a factor of 20 in frequency, and our driving decreases somewhat, but not too strongly.
No, my question was simply how this change in the intensity correlates with observations, whether the intensity in the bands is.
Yes, so intensity in the bands seem to be, well, it's not easy to measure because they do it not as a one observation in all the frequencies, but
I know, but nevertheless.
But generally, the bands, as you can see, they're pretty similar in intensity. But again, this is the question of already nonlinear saturation. And actually, in the paper, I argue that I give few explanations why even single particle intensity doesn't drop very quickly and actually is expected to start flattening or increasing at some point. But I didn't do it too much because this is just the first step of linear driving. Basically, you know, at higher resonances, the argument of your Bessel functions become larger. So that means you're raising, though you're raising it to a small power, but the argument is larger. So that's give you larger power.
Okay, can you clarify what you mean by driving then? I mean, I think that's the key point here.
By driving, I mean that this is the picture for single particle emission. And then on top of that, you have to add phases from single particles and then average those phases over whatever you think is important.
No, wait. You're saying linear driving, nonlinear driving. What do you mean by linear driving, nonlinear driving, weak driving?
Oh, the amplitude. So the what is important for driving is actually not the ratio of the fluctuating magnetic field over constant magnetic field, which is very, very small, but fluctuating field divided by the guide field times Lorentz factor. So, and even ratio of fluctuating over guide field times Lorentz factor may not be that small of a number. Still, I assume that it is small, and in an approximation it is very small, then I call it linear driving. But if this starts to be of the order of unity, then it's kind of nonlinear. Then you may start to start exciting gyration.
Okay, so let me disentangle that. So you're talking about the motion of a single particle, so that you put some wave-like driving on the right-hand side, time dependent, and the amplitude in front of it you call linear or nonlinear, depending on whether it's less than unity or greater than unity, and this is delta b over b times gamma squared, or times gamma.
Times gamma, yes.
Times gamma.
Yeah. Basically, this is the amplitude of oscillations in speed of light. Mm-hmm. Gamma times the ratio of the driving of the wiggler over guide field.
Okay.
And it's important that it's not just the ratio, because the ratio is very, very small, but you multiply it by gamma, so that makes it not that small.
Okay, and can you get delta omega over omega of what, a 6% in this case? How?
This is my reasoning. I haven't calculated that yet, but 6% is the next order effect I think. And as I said, there is I see two ways to go. First, saturation, and then the nonlinear Matthews equation. When nonlinear driving, this tons, they move to higher frequencies a little bit, so that's kind of goes in the right direction.
Well, if you're effectively talking about back reaction, then.
Mm-hmm. Well, that would be the saturation.
Saturation is back reaction.
Yes.
Okay. Yeah, I mean, usually saturation is determined by synchrotron losses, right? In actual.
Oh, it depends. I don't know.
No, there is no
losses here.
Yes.
Yeah, there is no synchrotron losses here.
Well, I mean, in the high gain FEL, it's one of the limiting factors.
Yes. So
you cannot beat it.
Here is what I said, that this is a very wrong way to think about, but it works. Here I just said, let's put a fraction of the beam energy into radiation and my brightness temperatures come out right. But eventually the saturation will be probably it's the destroyed coherence. The back reaction will destroy coherence. That will determine the saturation level.
Okay, then it's easy to say that higher frequencies will be destroyed faster.
They should.
Because they were multiples of
Right.
the fundamental frequency.
Right. But then faster, but maybe they, yeah, anyway, it's, yeah.
By the way, can you get a 30 microsecond pulse from this thing? You know, like.
Yeah, I guess, oh yeah, that's actually at the very bottom here. Duration we expect from micro to milliseconds. And again, by energy, we need about a football field to power X-rays, so which is 1/100th of a neutron star radius. Then if you imagine this active region, the shortest that it can work would be a light travel over 100 meters, which is microseconds. But the longest is that if you have this region and it sweeps due to the rotation, but it is operating longer than that. But this sweeping will take 1/100th of a period, and this now goes to milliseconds. So yeah, from microseconds to milliseconds.
I wonder if you produce it over 100 meters, then how do you squeeze the wave with the characteristic k of what 1 over the radius?
Yeah, so of course, this 100 meters come from taking the energy in the X-ray burst, taking magnetar magnetic field, and asking how much energy you need to use.
Okay,
so
what's your emission length?
Yeah, so again, this is a very rough and rude attempt at placing these microphysical models into macrophysical.
No.
But I don't want to push that because this is likely to fail. Yet just a general scaling, it seems consistent.
No, that's a very simple question that I'm asking. You have a certain length in a laboratory frame over which the FRB or whatever pulse is produced, right? So you have certain emission length, let's call it that way, whatever it means. And you need to squeeze in there many oscillations of your alphane wave. So if your alphane wave has a wavelength of what are the neutron star radius, then the total length is going to be the number of oscillations times that wavelength.
Yeah.
Real big. I mean, it's not going to be near the surface. It's going to be somewhere outside.
Not exactly. I don't quite agree because, say, the example with a Gaussian pulse. So it's just a bunch of charges shaken once, and they're shaking, but because it's a bunch for the wavelengths longer than the size of the bunch, this single shaking adds up coherently.
Oh, and you misunderstood what I'm not probably explaining it that well. What I'm saying is that you have your wiggler sitting there, and you have a bunch or whatever certain number of particles going through.
Yes. So
they start here and end up there. That's the length of your wiggler, and
right.
Your wiggler has to have a number of oscillations in the field. If your wavelength of a single oscillation is the neutron star radius, then you have n neutron star radii, which is going to be probably 100.
Yeah.
Then you cannot squeeze it within the magnetosphere at the radius of a neutron star radius. You have to move outwards.
Maybe we're going in circle, but as I just said, the wiggler does not have to have many oscillations. A single Gaussian pulse will also produce broadband coherent. It was a bit surprising to me, but it worked.
No. I'm talking about just the scales. I mean, it's either a wave that's moving. In that case, if you have a wave that's moving, passing by a bunch of particles, that's fine. Particles are sitting there and the wave is passing by. But if your particles are moving through, they need to move through a certain distance.
Yes.
Yeah, I think make it mostly just that distance surely is not 100 meters, right? Or
Well, that's right. I mean, first of all, it should be at least a neutron star radius.
Yes.
But in
Yes.
fact, many neutron star radii.
No, I don't think why.
Because otherwise, it's not a monochromatic wave. Or even if you have a Gaussian pulse, Gaussian has a certain width, and you're
Yes.
saying width is small,
Yes.
which means you have a certain harmonic there, and you need
Yes.
space to fit that harmonic in the magnet.
Yes, but that width can be 100 meters if you fish. But again, this 100 meters come from X-rays, but basically it's this idea of 100 meters is the region can be fairly small. And again, if you have a Gaussian pulse of 100 meters, then
I think we're talking about, seems to be talking about two slightly different things. So I can see that you have this region of 100 meters which reconnects and releases a whole beam of particles. And I think Mikhail's question is, how far does that beam travel before it has emitted?
That's right, exactly. Thank you, Mark.
That was my point before, Maxim, that you need the 10 stellar radii, I say, for at least for the Wiggler, by which your field will change, as you know, with radius.
But that may in itself not be bad, actually. I'm not worried, who knows, maybe you can arrange it, but is it true that you need to, as you're sort of adding up all this emission, you are traveling quite a bit, or not?
Yeah. So again, this picture of Gaussian pulse. So let's imagine we have a region of 100 meters that generates a beam. And let's imagine that beam encounters a Gaussian pulse, a Wiggler pulse, that is 100 meters long.
Oh, the Gaussian pulse is actually in the Wiggler. It's not. See,
yes.
I completely thought that you sent out a Gaussian pulse of particles here, but
no, that's the Gaussian pulse of the Wiggler. So the Gaussian pulse has 100 meters. We multiply it by gamma squared. So here is your millimeter.
Maxim, I understand your Gaussian pulse is the envelope of your harmonics, right? So something goes up and then goes down. So this is the envelope. How many oscillations do you have for each harmonic within the Gaussian pulse? You cannot squeeze in a wave which has longer wavelength than the Gaussian pulse itself.
Well, as you can see in this simulation, well, I did it from 1/10 of a Gaussian pulse, so 10.
Right. So if your wavelength, I mean, if the length of the Gaussian pulse is 100 meters, you can squeeze in only something that's like 10 meters in wavelength. I mean, you have a box of 10 meters. How many oscillations within that box you have? If you at least.
Okay, well, we can go the other way around. Let's have a Gaussian pulse of 1 meter. So then you will have then a wavelength of 10 meters. We'll see so there is 1 meter bunch of particles that oscillates coherently. And all the waves with longer phases, with longer wavelengths, see this as coherent bunch did this.
No, the simple thing I treat this Gaussian pulse is that you have that's the box. I mean, you have nothing before, you have nothing after, and you have certain size where you have some wave activity.
Yes.
Then you have a fundamental harmonic, then you have double that, triple that, and so on. The wavelength of them are smaller than the size of the box.
No, yeah, well, smaller than the size of the
delta
ball,
function actually.
but they can be larger than the width of the pulse. And that's what
right. So when you're saying it's 100 meters, the wavelength of the harmonic cannot be larger than that.
No, I think Maxim is thinking more about almost a delta function. If you hit a string of a guitar with a an impulse, like it will ring at a much longer wavelength.
Right. Yes.
Oh, that's a different thing. There you have the whole guitar resonating.
It's irrelevant comparison.
No, hold on. So here, what I do, I have a box which is large, and I have a particles there. I shoot a Gaussian pulse through. The width of that Gaussian pulse is much smaller than the size of the box. That pulse passes through. I take.
Do you have activity before or after the pulse?
No, nothing before, nothing after. The pulse passes through. I have particles seated there. I track phases as each particle emits, and I add those phases.
I mean, I see no problem with that. My question then is, okay, you have certain size of a pulse, and you have, I mean, if it's a monochromatic, you just say, okay, that's some certain monochromatic wave that fits in such a region, and then it moves through, and the particles see that changing field. But how many oscillations do you have here? That's the question of kW that you have here.
Yeah. So as I see, I go to 0.1. So my pulse is about 1/10 of my box. The pulse width.
That I don't understand that.
I have a box of 10 and a pulse of 1 passes through.
By box, you mean the entire magnetosphere?
Well, by box from which I take, I have to limit my, I have a string of particles.
Okay.
And so I need to calculate coherent addition. So I need to limit, yeah.
Okay, let's define here. I'm not talking about your simulation box. I'm saying that if you take your pulse, this is the box, because everything else outside is irrelevant. I mean, how it moves, that's another way, but I can always just focus on that box, and I can let particles go through. That's exactly the same. I just change the reference frame, right?
Okay, but your box should be much larger than the pulse.
Okay, my simulation box can be infinitely large, but there are no waves there, so I don't care about those parts. Particles just live there on the right. Particles live there on the left. That's fine. But you have a certain place where you have your oscillating alphane wave.
Yes.
And you let particles go through.
Yes.
Let's just focus on this.
Yes.
The size. This is the size of the box in my definition.
Yes.
Because that's the only place where certain activity is happening.
Okay.
Right. Then I want to ask, what's the wavelength of a harmonic that you can fit in this box?
No. Hold on.
Because this is kW.
I think we should actually stop. I think your guys are talking a little bit past each other, and I see people dropping off. It's quite late. I think maybe it's good to sort of think both and see. Probably one of you is making a mental thing. I'm not sure, Room. I'm certainly unable to judge.
That's
but
right. Yeah, I'm sorry to totally dominate.
No. That's good. I mean, I think this is right. It is. It's partly just Maxime is presenting something quite new, at least for me. And my mental picture, as I said, I thought we're talking about the Gaussian pulse of particles. So I clearly had the wrong mental picture. Yeah. It's the Gaussian pulse of magnetic field disturbance, is that?
Right.
And I hope I can
the Gaussian pulse
if I don't
of
understand
disturbance and a string of particles.
Yeah.
Constant string of particles.
Okay, well, thank you very much, Maxime. I thought it was very exciting, and I'm hoping to challenge your picture with our crab giant pulsars at least.
Yes.
Okay, so again, thanks again. Thanks also for everybody, for all our visitors from abroad, more or less, and from far things to turn up. And see you all. Yeah.
Yeah. Good. So Amir, I would like to follow on our discussion, and
Yeah.
And Misha too.
Okay, but
but not right now because we're disconnecting.
Yeah, sometime, of course. Thank you very much.
Yeah, thank you. Bye
Good.
bye.
Thank you for listening.
thank you, Maxim. Bye.
Bye-bye.
Thanks.